And so just remember for a moment that a rate is equal to the change in the product concentration over time. And so thinking about that, how we write rate laws here, we want to look at the change in product concentration over time. Well, the rate laws, we always write whatever concentration term is at the tail of the arrow, right? So ES is the tail of the arrow, so that's going to be a concentration term involved, and whatever rate constant is above that arrow. So the rate law for this is going to be kcat times the concentration of the enzyme substrate complex. Now, because this system has been done under special conditions, right, where this scheme only holds true early on during the course of reaction, we're actually going to call this something more special. We're going to call it VI for initial velocity, or also sometimes people call it V0 for the velocity at time 0. And so let's just rewrite that very clearly. So the initial velocity of an enzyme reaction is equal to kcat times the concentration of the enzyme substrate complex. We're going to call this equation 1. Well, that's a little bit of a problem. The whole goal of this is that we can measure a rate and we can get some useful parameters out of this that tell us something about the enzyme. But we don't really know what the enzyme substrate complex concentration is at a particular time. We cannot really measure that. So we need to re-express this in terms of things we can measure. We can measure the substrate concentration. We know how much material we've added to the test tube. We know how much enzyme we put in the test tube as well. So we have to re-express this equation somehow. And we're going to make an assumption now called the steady state assumption. The steady state assumption, to understand, let's look at, again, concentration as a function of time. And we're going to look at 3 different species this time. We're going to look at substrate. We're going to look at product. So at time 0 here, right, we know that product is going to have 0 concentration. The enzyme will have a low but non-zero concentration at time 0. Again, we're kind of zooming way in compared to the other plot. The substrate, as reaction goes, of course, will decrease. We're not going to worry too much about substrate, but that'll start to go down. Okay, and we also know that product concentration will start to go up. We're not, again, too worried about that. But what's important to understand is that the enzyme concentration will change. Initially, it's just the free enzyme. However, very quickly after we combine enzyme and substrate together, the free enzyme concentration starts to decrease, keeps this steady level, if you will, over time. And then another species, the enzyme substrate complex, is 0 to start, but it increases and then achieves some level like this, whatever it happens to be. That's the enzyme substrate complex, ES. So the whole point about this is that initially the enzyme substrate concentration is 0, but after a very quick time, and we're talking usually about milliseconds of time here, the enzyme substrate concentration is consistent over time. In other words, its change in the substrate, the change in the enzyme substrate concentration is 0. And so we can rewrite that as the following. We can say that the change in the enzyme substrate concentration over the change in time is equal to 0. And so this is going to be the whole basis of what we're going to call the steady state assumption. And so essentially, whenever we are within this time frame here, we're within the steady state. If we're before that, notice that before that the concentration of the enzyme substrate complex does change. That's called pre-steady state or burst kinetics. That's not what we're going to do in this class. That's some fancy stuff. So like I said, our goal is to develop an equation that will tell us some useful parameters if we plug in values that we know and can measure. which talks about the enzyme substrate complex. And we're telling it that it's not going to change over time. But let's sum up all the different reactions that affect the enzyme substrate concentration. So I'm going to draw the scheme, right? E plus S make the enzyme substrate complex via K1 and K minus 1, and produce the enzyme product free via Kcat. So we want to explore what's going on with the enzyme substrate complex and ask how does its concentration change over time. So we want to ask d ES over dt. Okay, well, there are a couple things here. Notice that there's one arrow that points toward the enzyme substrate complex in the scheme, and it is the formation of enzyme substrate complex from free enzyme and free substrate via K1. So that's going to have a positive influence on the production of the enzyme substrate complex. So we're going to have a positive value where K1, again, remembering how we write rate laws, I've got K1 is the arrow, and then I write the things, the concentration terms that are at the tail of that arrow. I've got free enzyme times free substrate, so it's a second order rate constant. And then all the other things that are arrows that are affecting ES are going away from it, right? So they're reducing the concentration of ES. So these are going to be negative terms. So I've got minus K minus 1. So this is the enzyme substrate complex falling apart to free enzyme and free substrate. But it's first order because there's only the one ES term there. I also have the Kcat term removing enzyme substrate complex, so we're going to subtract Kcat times ES. And what we're going to do is I'm going to rearrange all of these terms, and I'm going to solve for ES. So I guess this is my little rearrange squiggly. So the concentration of the enzyme substrate complex, if you go through and do all the algebra, you'll find the following. It's K1 times free enzyme times free substrate divided by K minus 1 plus Kcat. We're going to call this one equation 2. So we have re-expressed ES in terms of other things. We know how much substrate we added to a reaction. We don't really know how much free enzyme is in there though, so we need to somehow figure out and relate this free enzyme to total enzyme, because some of the enzyme is bound up in the enzyme substrate complex, so free enzyme is a tough one to figure out. So let's re-express, and the way to do this is to inventory all the possible enzyme forms. So we've got total enzyme, that's how much I know I squirted into the test tube to do the reaction, equals free enzyme plus the enzyme substrate complex concentration. This one is equation 3. All right, so now we have a way to express the free enzyme in terms of other things that we either know for sure or have already expressed. Okay, so a step closer. So now what we're going to do is divide equation 1 from a couple pages ago by equation 3. But we're going to do this in a clever sort of way. So remember, equation 1 was initial velocity equals Kcat times the enzyme substrate concentration. And so to divide equation 3, I'm actually going to divide it like this, where I've got total enzyme concentration, right, equals the sum of the two forms, free enzyme and the enzyme substrate complex. This is equation 4. So now we have this enzyme substrate complex term. Can we we already re-expressed that earlier on. That was equation 2. So now let's substitute equation 2 in here. And there would be a series of cancellations. I challenge you to try this on your own. Put equation 2 in for ES and see if you get the same thing here. So what I end up with is, again, this initial velocity divided by the enzyme total enzyme concentration equals, we still have the kcat on the top, but now there's, because of those cancellations, we just have substrate concentration. And here we've got k minus 1, and we've got kcat divided by K1 and plus the substrate concentration. So I left off a number of steps there. I challenge you to go through and try those cancellations on your own. Now notice that this whole term here, this K minus 1, kcat, K1, those are all describing what's going on with the enzyme substrate complex. K minus 1 describes the falling apart of the enzyme substrate complex. Kcat describes the formation of product. And K1 describes the formation of the enzyme substrate complex. So we're going to sort of collect those all, right, into one thing we're just going to call Km, capital Km, which is known as the Michaelis constant. And that leaves us with the following: initial velocity divided by the total enzyme concentration equals kcat times substrate concentration divided by now this Km plus the substrate concentration. Now that's good, but remember the point of this whole thing is that we want to be able to have things that we know. So we know how much enzyme goes in, we know how much substrate goes in, and we're going to measure the rate of the reaction. But we kind of have that over here with initial velocity, but really what would be better is if we could get rid of this free enzyme term. And so we can multiply both sides by enzyme total. And this identity we'll look at later on here is that if we multiply kcat times ET, that gives us this new parameter called Vmax. And we'll explore what that is. So now multiply both sides by that, and we end up with initial velocity equals Vmax times the substrate concentration divided by Km plus the substrate concentration. This is the Michaelis-Menten equation. Notice that we have things that we know or can measure. We know how much substrate goes into the reaction. The total enzyme concentration is buried within Vmax, and it all is equal to the reaction rate, which we can measure in the lab.